As we continue our conversations about the fundamental theorems of calculus, last time we proved the first part of the fundamental theorem, and now we're going to lead into the second part of the fundamental theorem of calculus. But I want to start with an intuitive example. So suppose we were given this table of values. We've had something like this before, some various times in seconds, and then the velocity at those various times. And suppose we were asked to find let's say, left Riemann sum. So the Riemann sum of the left endpoints. All right, well, this is a pretty easy one because the intervals, all the widths are size 1. So we have, width of 1, and then f of 1, the left endpoint would be 2. And let's think about the labels here. So 1 is in seconds, and then this would be my velocity in feet per second. And the next width, again, is 1 second times its velocity with the left endpoint, 4 feet per second. And so on. So each of these have a width of 1, and I am using the left endpoints. And so I would end the last interval from 4 to 5, width of 1, and then the velocity of 8 feet per second. So that when we add this one up, this is pretty nice numbers here, we would end up with 20. And then when we think about the units in this case, we can look at how essentially when we multiply velocity times time, this is a pretty intuitive idea that you get the distance. So distance equals rate times time. That's kind of what we're doing here, right? So we would end up with our label here as 20 feet. And we talked about this interpretation. So this is an approximation for the net change. So this is the approximation because it's a Riemann sum with just, 4 subintervals here, 4 rectangles if we were to graph it. So it's an approximation for the net change in distance or position over this interval, from 1 to 5. 1 to 5. All right, now suppose we were to do the right Riemann sum. And so widths are still just all 1, so this gives us a chance to review these Riemann sums as well, although we have an equal width case here. But this time with right endpoints, we would start with f of 2, so 4 feet per second. And again, each of these have a width of 1, so all the widths are pretty easy here. And then using the right endpoints, we end the last interval with f of 5, and that is 10 feet per second. And so once again, when we think about these units, each of these are estimates for the distance traveled in each of those 1 second intervals. That's what each of these terms represents. And so in this case, it looks like I end up with 28 feet as my approximation. Again, both of these are approximations for the net change in distance over this interval from 1 to 5. And in fact, if I were to, let's say, think about the graph of this one, so you don't need to go up, whatever. And it looks like, extend that a little bit here. Velocity is going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4. So this is 5 in here. And then on my 1, 2, 3, 4, 5. All right, so maybe I didn't need quite that much up here or over here. Or I could have made it a little bigger maybe. All right, so what do we have here? So at 1, we're at 2. At 1, we're at 2. At 2, we're at 4. At 3, we're up at 6. At 4, we're up at 8, and at 5, we're up at 10. So pretty quickly, we can kind of see what we have going on here. This happens to be just a really nice function to work with, right? Looks like it's really just the velocity function. We're going to make our leap here and say that this is the function 2t. And so, I mean, technically I only gave us, but now I'm just going to fill it in and say, yes, in fact, that is what this function is. So what were we just finding here? We had looked at the interval really from 1, so right here from 1, and then over here to 5, so from 1 to 5. And we were looking at both the left and the right endpoints. But we were looking at rectangles, right? We had divided it into this partition, and so what we were finding was an estimate for this area under the curve. And so we have both an overestimate in the one case, so if we were to look at the left Riemann sum in this case is a lower estimate. If we were to look at our right Riemann sum, this is giving us that overestimate. All right, and so we know the actual area is going to be somewhere in between 20 and 24. And so we kind of know this game, right? So what happens if we want to find it exactly? We would have to set up the letting the limit as n goes to infinity, the limit of the Riemann sum. So if we no longer wanted this approximate change for the net change in the distance, if we were really going to look for then the actual, so if we wanted the actual this time, net change in the distance over this interval from 1 to 5, well, we kind of know how this works, right? It's not just using, what do I have here, 4 rectangles. Instead, it's letting the limits, let the number of rectangles go to infinity of the sum as I goes from 1 to n of my function, which is 2 times, and then my representation, if we remember how this works for the c sub I. So if we remember this, that representation was the a plus I delta x. So the a in this case is 1 plus I times the delta x. So remember delta x is the b minus a over n. So 5 minus 1 is going to be 4 over n. And so the I times the delta x is the 4 over m. And then times that delta x. So this is the limit of the Riemann sum. So we did this many times. So I think this one's relatively quick. I can even just squeeze this in here now that we've done this a few times before. Let's bring both the 2 and the 4 over n. Those are both constant multiples that we can bring in front here. So let's bring that in front. So that's my 8 over n times the sum as I goes from 1 to n of, and we can break this really now into 2 terms of just 1, and then plus the sum as I goes from 1 to n of the, and I'm going to bold this little 4 over n, that guy right here in front, and then times I. So I'm kind of squeezing this in, I know, but I just wanted to kind of go through this. We've done this before. So sum as I goes from 1 to n of 1 is just going to be 1 times n, which is m. And then the sum as I goes from 1 to n of I, that was that n times n plus 1 over 2. And we're looking at the limit as n goes to infinity of 8 over n times that quantity. Well, if we do that, we're going to have in the first term, if I distribute through, I'm going to have limits as n goes to infinity of just 8. And in the second term, if you want to do some reducing, I mean, I guess we could at least reduce those n's if we wanted to. If we wanted to reduce the 4 and the 2, we could. We don't need to. we do need to distribute through our 8 over n though. And so the 8 times the 2, it looks like we would have a 16 times the n plus 1 over, and then just looks like that n. And if degree of numerator is equal to degree of denominator, this is just going to be, as n goes to infinity, ratio of the coefficients is 16. And so we find out, not surprisingly, the actual area in this case under the curve was 24, kind of halfway in between our lower and our upper sum, or our left and right sum here. So 24 feet is going to be the actual change, net change in distance. So this is the actual net change in the distance because we let the number go to infinity. Okay, so this is, I mean, you're probably wondering, like, when are you getting to the fundamental theorem of calculus? And I'll be honest, I'm starting to wonder too. So anyway, so that's kind of what we had, and we have done that before. Okay, now I want us to think about, I'm talking about the net change in the distance function. Well, let's just kind of pull this together here. And I'm going to tell you, not surprisingly, we talked about antiderivatives in the last section of chapter 4. So if the v of t function is 2t, then let's talk about what the s of t, the antiderivative function, would be. So that would be 2t squared over 2, which would just be t squared, and then potentially some constant. But let's just, for purposes of what we're going to talk about, we're going to have that s of t here is going to just be t squared. So here's really the premise of this example I'm giving you. We have a position function, s of t equals t squared. We had its rate of change, its velocity function, which was 2t. We have seen that through a Riemann sum, we can either approximate or take the limit of the Riemann sum. Once we take the limit of the Riemann sum, we get the actual change in distance or change in position. Actually, I kind of like the phrase position. Change in distance sounds kind of awkward to me all of a sudden here. So let's call this the change in position. All right, so we're looking at the fact that we can use, oops, I did not mean for that to erase all that. So approximation for the net change in the position over that interval. Okay. Now, I have another way to find the change in position. If I actually have the position function, which I do, so if I wanted to find, once again, the actual net change in position, then again over the interval from 1 to 5. Now that I have the actual position function, we could just say that would be s of 5, the end position, minus the first position, the initial position at 1 for this interval. So s of 5 would be 25, s of 1 squared would be 1, and we would get 24 feet. This is the fundamental theorem of calculus part 2. What it says is, and once we connect these two, and we know that the v is our derivative of s, so s prime is equal to v, or to say differently, s is the antiderivative of v. But essentially, if I want to find, so pulling these two things together, if I want to find the actual change in position on this interval from 1 to 5, then I could just do s of 5 minus s of 1. And what is s? S is the antiderivative of the v of t function. So these two things are equal. All right, let me highlight what two things am I talking about that are equal here. Let's highlight with this color. Okay, so what two things are equal? So we're talking about being able to evaluate s of 5 minus s of 1. And if we go back here, when I wrote out this limit of the Riemann sum, guess what? This is our definition of the definite integral on the interval we were from 1 to 5 of our v of t function. And v of t, we know, is also just s prime. The derivative of position is velocity. So when we were writing out the limit of the Riemann sum, that is our definition for the definite integral from 1 to 5 of what was the function here? It was v of t. V of t, we know, is the same thing as the derivative of s, so s prime. So what we are saying is equal is if I want to evaluate the definite integral from 1 to 5 of s prime, I can do that by finding the antiderivative s and evaluating between the limits of integration. So let's bring this down here and notice what I have here kind of in this specific example. So from our above example, we were saying, okay, the integral from 1 to 5 of some function s prime was equal to its antiderivative s, and that was evaluated between s of 5 minus s of 1. That is what this is saying in general terms. If I have some function f and I know its antiderivative capital F, then I can evaluate capital F of B minus capital F of A. So that's sort of the intuitive development of our fundamental theorem. If we wanted a slightly more symbolic, I guess I would say, maybe not so formal, but symbolic proof, let's just kind of quickly go through what we have outlined here. So we start off from the way the original theorem is stated, and we start off letting capital F be an antiderivative of lowercase f. And our goal is to prove this above statement here. And so we're going to go back to that definition from the first part of the fundamental theorem, where we define capital I of x to be essentially the area under the curve from a to x of f of t dt. So we did that in the first part of the fundamental theorem proof. So if you remember that, that was from part 1. And what we were able to prove from fundamental theorem part 1 is that the rate of change of that area is equal to the value of the function at that endpoint of that region. All right, so what does this tell me? If capital I prime is equal to f, that is the definition of I being an antiderivative. So I is also an antiderivative of f. So here's the thing. If we know that both f is an antiderivative, capital F, and I is an antiderivative of lowercase f, then they have to be equal except perhaps differing by a constant. That's if you have two antiderivatives, they have to be the same except potentially differing by a constant. So let's say capital I has to equal capital F except for differing by, let's put in our plus C here, differing by some sort of constant. Okay, so now suppose I sub A into this function. That tells me A, capital I of A would have to equal capital F of A, and then plus this arbitrary constant. Now, by the definition, so up above what I have underlined up there in yellow, so by my definition up here of capital I, So we know capital I of A, by definition, is this integral, this definite integral from A to, and then I'm subbing in this A. So this is my upper limit, that's how the function is defined, of the f of t dt. Well, guess what? One of our properties of definite integrals says that if your upper and lower limits are equal, you end up at 0. Your delta x, b minus a over n, is a minus a over n, and that's 0. So if I sub a into capital I would get 0. All right, so by the above two lines, what we have just shown, so by, let's say, these two lines here. So by this line, capital I at evaluated at A, and then this line as well. So these are both equal to each other. So by those two lines, what I have to then know is that the 0 has to equal capital F of A plus C. So that means C has to equal, subtracting, minus capital F at A. All right, well, going back up to here, capital I of X was equal to capital F of X plus C, and C is now minus capital F of A. So what we have just shown is that capital I of X, which again, by the up above definition that we kind of started with up here, so this is our definition for capital I right here. We have just shown by the last line of our work right up above, we have just shown that that is equal to capital F of X minus capital F of A. And so capital F is the antiderivative notation of lowercase f evaluated between our limits of integration of the x and then minus of the a. And so if I was using the x, if we replace x with the letter b, what we get is the definite integral from a to b of lowercase f of t, is equal to its antiderivative capital F of b minus capital F of a. So that's a little bit more of a symbolic way to go through a justification. It does rely somewhat on the proof we did last time, the first part of the fundamental theorem. Maybe what's more intuitive than that is kind of just going back to two things that we already have pretty good knowledge of and realizing the connection between those two. So this is extremely powerful. What we now have is a way to evaluate a definite integral, and by the way, make this prime a little more significant. For some reason that didn't paste through very, very well there. So what we now have is a way to evaluate a definite integral that doesn't rely on either geometry or that formal definition, the limit of the Riemann sum. We now have a way to do this that does not rely on that. It's telling us, hey, all those antiderivatives that we talked about at the end of chapter 4, I can, in order to evaluate a definite integral, I can figure out that antiderivative, and I can then evaluate between the limits of integration. And when I form that difference, that is going to give me what the definite integral is. And so that's what we've ended with, and that is pretty powerful here. All right, so let's just maybe look at one example here to end this video, just so we've looked at one concrete example, and then we'll come back and do some more next time. So number 1, so what has all this allowed us to do? Suppose I have the definite integral from 1 to 2 of x cubed plus 4x minus 1 dx. So the second part of the fundamental theorem says as long as, we have a function that is continuous on the closed interval from 1 to 2, which we do need the continuity there. Essentially, all I have to do is first take the antiderivative. So the antiderivative of x cubed is our x to the 4th over 4, plus antiderivative of 4x would be 4x squared over 2, minus antiderivative of 1 is 1x. And of course, you could do some reducing on that second term there. And then what we often use is then at this step, we drop the integral notation because we have taken the antiderivative. We've evaluated that, that function into its antiderivative form, so the integral notation goes away. But we do still need to evaluate between our limits of integration. So no more integral symbol, but a lot of times we would write it this way. And we'd still kind of have that 2 and the 1 here. And a lot of instructors may even say x equals 2 and x equals 1, because that's what we're subbing in. So this whole thing, this is your antiderivative capital F of x. And so now, so that was the first step. And now you can simply sub 2 into that antiderivative and subtract from that what you get when you sub 1 in to that antiderivative. Okay, so what does that look like here? So 2 to the 4th, so our 16 divided by 4 would be 4, plus, and of course we could have reduced that, so 2x squared, so 4 times 2 is 8, minus 2, so subbing in the entire, that value, minus the entire value when you sub in 1. So this is going to just be 1/4 plus 2 times 1 squared is 2 minus 1. And so this is going to be 12 minus 2, so this is going to give us 10. And so we're going to have 1 plus 1/4, so this is going to be 1 and 1/4 in here. And so 8 3/4 would be the value of this definite integral. So next time we'll come back and we'll do some more examples of applying our fundamental theorem of calculus here, part 2. We'll do a few more examples of this next time.